Okay, I was thinking about this yesterday. It's a math problem that was found on an Egyptian tablet. And the interesting thing about it is the method that the Egyptians used to solve these kinds of problems. They didn't have algebra to work with, and so they used a different method. So the problem is, the problem that was posed was a number plus a seventh of the value of that number is equal to 16. And we're looking to find the value of the number. So what the Egyptians did is they just chose a starting point. So in this case, an easy starting point might be 7. They said, let's just use 7 in this problem and see what we come up with. So if we start with 7, well, 7 plus a seventh of that value is equal to 1. Well, that's going to be equal to 8. And they knew that they could use ratios to solve this problem. So the answer that they're looking for is 16. And they knew that going from 8 to 16, we would use the same ratio to get from 8 to 16 as we used to get from our original guess, our original starting point, to the answer. So in order to get from 8 to 16, we multiply by 2. So if we multiply 7 by 2, it's going to give us 14 plus what's a seventh of our original value. 1/7 of 14 is equal to 2, and that gives us the answer that we're looking for, which is 16. So the reason why I was thinking about this at work is I can sort of intuitively understand the idea of ratios, but I was sort of wondering how in the heck they figured this out. And what I came up with is the Egyptians knew a lot about triangles. They didn't know anything about algebra or Cartesian coordinate systems, but they knew a heck of a lot about triangles. They'd actually used triangles to calculate the area of a circle, and I think they had access to the Pythagorean theorem, although I should probably look that up before I say they did. But in this case, all they needed to know was that ratios of triangles remained similar to each other. So if you had a similar triangle, let's say this triangle has a length of 4 and a height of, we'll just say 2. Okay? If you took that same triangle and you made it, you extended it, you made it bigger, okay? These ratios always stay the same. So if we made our length instead of 4, we made it 8. Now we knew that with a similar triangle, with a length of 8, we knew that the height, we doubled the length from 4 to 8. We also knew that the height would double, so it would go from 2 to 4. Okay, so let's turn this problem here, this problem, into a triangle and see what we can come up with. So we are going to use the length as the number that we're guessing. Okay, so let's say, okay, let me see if I can draw this triangle correctly. So if we had a triangle and we said, okay, let's just say that our length of our triangle is 7, the height of our triangle is going to be 7 plus its seventh, so the height of our triangle is going to be 8. Did I draw that right? It's close enough. Okay, so the height of our triangle is 8. At least we're getting the same ratio here, so we know that this is, the length is 7, and the height, or the length is length, and the height is that length plus its seventh. So in this case, we'll go 7 is length, and the height is 7 plus its seventh. That's equal to 8. Well, the answer that we're looking for is 16. And so we know that the ratio 7, oh, this is, okay, the ratio 7 to 8 is going to be the same ratio of number that we're looking for, the ratio of the number that we're looking for to 16. And so essentially they turn their word problems into a problem of triangles. And we can see that let's see, we go from 8 to 16, we have to double it, and we go from 7 to the number, we have to double 7, and it'll get 14. So Anyway, this is something I was thinking about at work yesterday. Instead of doing the multiplexers and routing circuits that I was supposed to be testing, and I was pretty happy with the explanation I came up with, so I thought I'd share it here. Alright, have a good day, guys. Bye.